since this is the last presentation, I will try to be brief. And so Windows take about 30 to 40% of account for like 30 to 40% of HVAC energy loss in buildings. So that is a typical building. If you have more glass, this loss is much higher. And if we talk about overall energy usage in the United States, they account for about 4% of the total energy. So when we are moving towards zero energy buildings mandate, is there a way that vacuum insulated glazing actually can be one of the enabling technologies to achieve zero energy? So I am so at the University of Maryland, we are developing vacuum insulated glazing that is affordable. So somehow we are trying to reduce the cost of VIG and especially the capex that is required for any production line. So my journey with vacuum glazing started like about 5 years ago, when one morning I woke up a little cold and I figured out that this patio door next to my bed was probably the culprit. It was too cold. So being from heat transfer background, we thought that we should solve this problem. And together with Jung Ho Kim, who is a renowned scientist in the area of heat transfer, we looked into different ways to reduce the heat transfer to the windows. And finally came to a conclusion that vacuum, if you can create vacuum between the two panes of glass, that would be the best way to go. So in this presentation, I would discuss about general aspects of VIG, how they are manufactured. VIGs have been in commercial space for more than 30 years. So we would discuss like what are the challenges, why we don't see them around so much if it is 30 years old. And a little bit of summary of like what work we are doing at the University of Maryland. So as we know, vacuum glazing is highly insulating. You can achieve about R15 or U value of 0.07 with VIGs. And as comparison to a double pane, which is R2 to R4, and a triple pane is like R6 to R8, depending upon the low E coating and other issues. So if you compare it again with the walls, wall is like R15 to R30. So we are talking about trying to get as close to the wall as possible in terms of insulation. So the best way to think about VIG is to think about thermos bottle. So in a thermos flask, what you have dual wall metal cylinder, and in between the metal cylinder, you have vacuum, about 5 millimeter gap. So that is proven technology. You can put your coffee and it can remain hot for like about 24 hours. So can we put the same technology of that vacuum insulation into windows? So when you try to put it in windows, it creates several challenges. First is that you are talking about flat geometry, and trying to create vacuum in flat geometry is like very, very difficult. You need vacuum chambers like thick wall metal, and then you need a lot of reinforcement. And here we are talking about glass. So trying to create vacuum between the glass panes. Next thing is that bonding with the glass is challenging. Why? Because the level of vacuum that we require is 10 to the power minus 4 torr, which is 10 million times lower than atmospheric pressure. So at that level, your typical seals, polymer seals, PIBs, and epoxies, they don't work. They are so porous that you'll kill your VIG within a minute. So what you need two types of seals. Either it could be a glass seal, that is like ceramic seal, or it has to be metal seal. So this problem was very easy if you were talking about thermos bottle, because it's metal and you have to seal it. Now you're talking about glass, which you have to seal either with glass or metal. And that too at a very low cost. Another thing is that you have to hold that vacuum for 30 to 50 years, and it has to be transparent. So, as I mentioned, that it has been in research space and commercial space for more than 30 years. at the University of Sydney was the first one who created VIG. This is one of the first samples that they had. And now there are about 14 production lines around the world, mostly in China, Taiwan, Japan, one in Europe, and we are going to see some in United States. And there are research projects going on like us and some other research institutes. So how does VIG look like? So now in the first picture, you see that there are few components in VIG. So one is that there are 2 panes of glass. So glass is one. Then you have seal around the edges, that brown color. And as I mentioned that when you try to pull vacuum between 2 panes, they will immediately collapse. So in order to keep them separate, you need some kind of spacers. We call it pillars. So those are those light blue color pillars. And you have a port through which you can pull vacuum. So if you see the second picture is like typical VIG. And on the one of the corners, you will see that vacuum port. Another corner, you may see something called getter material. So getter material is another material. It's like pure metal, and it will keep acting as a pump so that any molecule of gas that comes out in its life throughout from the glass, that can be absorbed back into that getter material. Otherwise, if you don't have a getter material, you lose vacuum again within a minute or so. So VIG is dead. So why does VIG perform so well? So the reason is that if you see a double pane VIG, so there are 3 modes of heat transfer: conduction, convection, and radiation. So what we are trying to do is that instead of having that argon gap or air gap, you provide vacuum gaps. So if you have vacuum, it kills the convection heat transfer. Also, it kills the conduction heat transfer. So only heat transfer mode that you have is radiation. So radiation from one pane to another pane. And that you can kill using good low-E coating. So that's why you can achieve very high heat transfer, probably R30, R40. But you have got pillars. So those actually reduce or limit the thermal performance of VIG. So since you have to keep them 2 panes separate, so those pillars have to be about 20 to 60 millimeter apart. And those pillars actually act as thermal short, like electric short. They act as thermal short. So from one side to another, there is heat transfer. And then there is a limit how far apart you can have those pillars. If they are farther apart, it's much better. So in this picture, you can see the pillars locations. This is thermal image. So farther you are having those pillars, more is the R value of VIG. So you can achieve R value of like 15. Or if you're closer, you can go about like R5, R6, R7. So depending on the spacing. So what determines spacing? The strength of the glass. So if you have annealed glass, you can only go only have about 1 inch of spacing. You cannot go beyond that. As soon as you go beyond that, the glass will break when you pull vacuum. But if you go with tempered glass, you can have that spacing about 2.5 inches, and you have like R15 window. If you go farther than that, then since the glass deflects, it actually touches, the 2 panes touch each other, and they create another thermal short. So that is the best you can achieve is like 60 millimeter with a typical 1/4 inch glass. If you go thicker on glass, probably you can go higher, but that's the limit. So in this chart, we are talking about what is the limit on thermal performance of a VIG. So it's not only pillars, the edge effects are actually also dominating. So typically when you hear about a VIG thermal performance R value, it is only about center of glass, not overall window. So if you look at this picture, it's thermal image, and on the edges, since the 2 panes are bonded together using seal material, so your heat transfer from one side to another, and it's actually thermal short. So you are losing a lot of heat on the edges, but center is cool. Like in this case, the blue color is cool. So edges are conductive. And even if you have R infinity at the center of glass, like you didn't have any pillars, you didn't have any thermal radiation, Still the edges will account for a lot of heat loss, and you'll still have like R7 to R10 windows, unless you minimize the edge effect. So why do we advertise the center of glass? Because this is one way to tell how good the VIG. The better way would be that if you fix the size of VIG, the larger it gets, is better the thermal performance. The smaller VIG have more edge effects. Typically, edge effect is about 2 to 2.5 inch, 3 inch, 4 inch, like that. So, since there are 14 different production lines, there are a lot of variations in VIG as well. So, what are the variations? As I said, that there are only few components in VIG. So, you see the 2 panes of glass, the seal, the pillars, and evacuation ports. So, those are the typical variation. You can have annealed glass or tempered glass. You can have metal edge seal or glass seal. Similarly, some people have found a way to create invisible vacuum ports. So vacuum port does not exist, and in some it exists. You can see the vacuum port in those two pictures. And pillar geometries could be different. If you become more creative, you can have hybrid VIG. So in hybrid VIG, what do? You have a VIG and build it as an IGU. So another pane of glass, and then your R value, which was like R15, could go to R20, R30. If you're more creative, you put two VIGs together, like an IGU. So you see the thickness of VIG is very little, like you're talking about 6 millimeter to 8 millimeter overall thickness, maybe 10 millimeters. So the VIG looks like a monolithic glass, the single pane glass. So you can have two single pane glass and you get like R30 to R in that range, thermal performance, but it becomes more expensive. So what is the benefit? That you have lower edge conduction now because it's acting as an IGU, and you can replace directly with an IG. Now we talk about what kind of codes and standards are there if you want to implement VIG. So right now there is no STM or US standard, but there are groups who are working with ISO. So we have one ISO standard for VIG, 19916, and they are developing another two other codes right now. So this one was mainly to measure thermal and optical properties of VIG. So next one will be like durability. Can it last for 50 years? How do you test this VIG? So usually for IG use ASTM E2190. Somehow we are still trying to implement the similar code to VIG, but it's not exactly the same. VIGs are built differently. Their stresses, thermal stresses are different than IGs. So there has to be another way to implement this. So now, what are the applications? So usually right now, all the VIG that is being produced is going usually in historical buildings, because in historical buildings, you need single pane, and VIG looks like single pane. It can fit in the existing sash, for example. So it's very easy replacement. Storm windows, where you can add it as an additional window, and you can improve thermal performance. You can also use it for new constructions. And one another niche area is freezer doors. So if you go to supermarkets, you have freezer doors, and there the temperature difference between inside and outside is minus 40 degrees C, 24/7. So that is another area for VIG. So if VIG is so great, why don't we see them around yet? The main challenge is the cost. So cost versus performance. So you are getting performance, but what is the cost penalty you're paying? So if you see this chart, typically a dual pane window will cost you like $3 to $5 or $6 per square foot to manufacture. A triple pane will be maybe almost double of that. And current VIGs are expensive. So we are talking about somewhere between $20 to $30 per square foot. And this actually depends. This is like typical number. This depends upon how they are manufactured, how they are being priced, and it will change, I think, in future. So one is the cost. Ideal VIG should look like the dotted line, where the cost of VIG is closer to triple pane, but thermal performance is much better. Another challenge for VIG is that there is very limited installation experience. Some people have tried to put VIG in buildings, but only few, let's say, panes are actually changed. There are reliability concerns. So if you have a double pane and there is a leak, people probably will not notice until there is condensation or something. If there is a VIG, if it leaks, any leak will actually kill the VIG within a second, and you will have a single pane of glass. So all the glass will be there, but it will be a single pane. So the thermal performance is gone. So that is another concern, that our VIG is reliable. We have seen that in last 30 years, VIGs have been in the commercial space. So, but there are still like some issues that people are trying to resolve. Aesthetics is another concern. So as I said, there are pillars and there are vacuum port and there are getter ports. So some people don't like them. So you can't see the pillar if you are a meter away from the VIG, but if you go very close or you're against like a white background or something, you will see the pillars. So that is another concern. So there is a lot of research going on right now to improve the VIG and try to resolve those concerns, improve the reliability, reduce the cost of VIGs, somehow improve the edge performance, and develop the test methods and standards. If you're interested, Rob is probably the best person here who works with VIG. So what we are doing at the University of Maryland is we are trying to create low-cost VIG that can be developed at room temperature. So why VIG is so expensive? Is there some special material? No, it's just 2 panes of glass, a seal, and the pillars which are actually dirt cheap. So the major cost actually goes in the production process. So you take 1 pane of glass, put a seal around it, put some pillars, and put them together and send it in an oven to bake. That baking process takes 30 minutes to 2 hours, and then it comes out as VIG. If you stand at the end of production line for an IG, it takes like 20 to 30 seconds. Every 20 seconds, IG is coming out. And you stand at the end of production line for VIG, every few minutes of VIG is coming out. And the manufacturing capex, actually, tooling requirement is very expensive. So if you add them together, the tooling and low production speed, actually it adds up to a lot of costs. And we thought that, can we develop a VIG process where we don't have to bake? And it can be made just like an IGU at very low cost. So mainly we are trying to reduce the capex, and the way to do it is doing them at room temperature. So create that seal at room temperature. We are also looking into flexible edge seal so that we can reduce the edge conduction and also improve the reliability. So this picture at the bottom actually shows the comparison of 3 glass technologies. So dual pane is on the right side, the left side, and then you have typical VIG, and the third one is UMD VIG. So you can see from heat map that our VIG actually is performing pretty good. Our research has been funded by Department of Energy, NSF, University of Maryland, and State of Maryland. This is last slide. So we have also developed prototypes which are small right now at lab scale, and we send them to NREL for durability testing. And we have also been doing a lot of durability testing, weathering testing within our lab. And we also do thermocycling and thermal performance test. Thank you very much.
Pratnesh, a great work, really promising. Have you tried to see, at least initially, durability of the units? Have you tried to test for durability?
Yeah. So usually what we do is that we create whatever sample we create, we try to thermal cycle ourselves to extreme temperature. For example, one side is room temperature, another side we take it to 150 C and cycle it every 1 hour, like going up and holding it, coming down. So that is one test we perform. And then we send our sample to NREL which they test for ASTM, and it passed actually samples.
Okay.
So that is the process we use.
And do you envision technology being commercialized in sort of near future? Your technology?
So far it has been a university research within university. So now we are actually taking it out and spinning up a company called Next Class. And so I am moving out of the university to actually head that.
Oh, okay. Okay. All right. Thank you.
Thank you.